Hey everyone, we are back with another video for our differential equation course. So in this video, we will be doing second order linear differential equations, which means we have finished all of our first order differential equations and it's time for us to enter to the second order linear differential equations. Solving second order linear differential equations is a bit different with what you do or what you did in the first order ODE, whereas the general form is px y double prime or y double xn plus qx y xn plus rxy equals to g of x. So this is the general form of a second order linear ODE, and there will be three cases. The first case is where your second order ODE has two roots in it, and the general solution for two roots is y equals to C1 times e to the R1x, or the first root times x, plus C2 times e to the second root, or R2 times x. And for the second case, or case number 2, is where if your second order ODE only have one root, which the general solution for one root is y equals to C1 e to the Rx plus C2 times x times e to the Rx. And the last one, case 3, is when your second order ODE has imaginary root. And the general solution for case number 3 for complex number is y equals to e to the alpha x times c1 cosine beta x plus c2 sine beta x. And without further ado, today I will be providing 4 examples for each cases, but the first example I will be solving the second order ODE by definition, and you will know what by definition means when we get into the first example. But for the second, third, and fourth example, I'll be showing you the easy way in order to solve for second order linear ODE. So without further ado, let's go into the first example. Hey everyone, we are at our first example for second order linear differential equations. Okay, so solving this second order linear differential equation will be much more fun because it's way much more easier than the first order. And so we have here y double xn or y double prime minus 5y xn plus 6y equals to 0. And I put the three cases on the right hand side in case you forget. And so solving, we're gonna solve this second order linear ODE by definitions. And what I mean by definition is that y is equal to e to the rx. And we're going to need to substitute for our y double x and y. And so let's take the first derivative of y here, which this will gives us re to the rx. And our second derivative for y here will gives us r squared e to the rx. And now substituting everything into our second order linear ODE here, we will get r squared e to the rx minus 5 times our y accent, r e to the rx plus 6 times y, which is just 6 times e to the rx equals to 0. And so we can see right here that we can pull out all of our e to the rx outside, which e to the rx times r squared minus 5r plus 6 equals to 0. And if you see right here, we can solve r squared minus 5r plus 6 by finding the roots of it and determining how many roots it have from case 1, case 2, and case 3, and make the general solution by choosing from either case 1, 2, or 3. And so e to the rx right here has no root, okay? So it is undefined. So we just need to care about what's inside this bracket right here, okay? So we know that if we gonna solve this, we're gonna get r minus 3 and r minus 2. Because minus 3 multiplied by minus 2 is 6 or positive 6, and minus 3, minus 3 subtracted by 2 is negative 5 right here. And so our roots here, and this don't forget equals to 0, and don't forget our root here will be r equals to 3. This is r1, and for our r2 here will be just 2. And so we know right here that we have two roots. And so we know which case we're gonna use, which is obviously case number 1. And so let's use the general solution as our final solution for case number 1, which is y equals to c1. C1 is just C1, let it be, because C1 is just another word for constant number 1. So C1 multiplied by e to the r1, which is our r1 here is 3x, plus c2 e to the r2, which is 2 for ours here, times x. And so this is our final solution for example number 1, solving this second order linear ODE by definitions. Hey everyone, we are at example number 2 for today's second order linear ODE. So we have here y double prime minus 81y equals to 0. And we're not going to solve this second order linear ODE by definitions because I told you at the start of this video that I'm going to tell you a simpler and easier way to solve for second order linear ODE, which is if you see y double accent here or y double prime, just refer it as r squared. And if you see y prime or y accent, just refer it as r to the first, or usually we refer it just as r because we know it is to the first, right? And lastly, if you see y here, just refer it as a constant multiplication of 1. And so by knowing all of this, okay, let's move this to the side so you don't forget, at least for at the moment. We know that we have here y double accent minus 81y equals 0. So we can replace our y double accent with r squared here, okay? So we can rewrite this as r squared minus 81 times y. Y is just a constant multiplication of 1, so you don't need to write it, equals to 0. And you can see right now how easy it is to find the roots, or the solution roots to this equation. We can just subtract or add 81 to both sides, okay? Keep in mind, add 81 to both sides. This will become r squared equals to 81. And then we're gonna square root both sides here, okay? To remove the square on the left hand side here. And we will get r equals to plus or minus 9. Because the square root of 81 is 9. And you need the plus minus sign since it is a square root, okay? You don't just give it as r equals to 9, okay? And that will give you a wrong answer because you will choose case number 2, which only has one root, but in a matter of fact, this is using case number 1, which it has two roots. And so we know that our r1 here is just positive 9 and our r2 here is just negative 9, which our final solution using case number 1, general solution, we will have y equals to c1 times e to the r1x, which is positive 9x, plus c2 times e to the r2 times x, which is negative 9 times x. And so this is our final solution for this second order linear ODE. Hi everyone, so this is our second example, or our third example for today's second order linear ODE. So we have here y double accent plus 6y accent plus 9y equals to 0. And from the previous example, I've told you the easier way, I've explained it, how you do it. We can rewrite this equation become r squared plus 6r to the first plus 9 because y is just constant multiplication of 1 equals to 0. And from here on, it's really easy to find the roots for this equation, which we all know that the root to this equation will just be r plus 3 squared equals to 0. And can you guess how many roots it has and what case should we choose for this situation? Of course, we're gonna choose case number 2 because it only has one root, which r is equals to negative 3. And by then, we're gonna our general solution, I forgot to mention it, but from our previous examples, which are example number 1 and example number 2, and this example number 3 and later example number 4, we're going all of our answers or solutions are in the form of a general solution, okay? Because it has no initial condition. So our back to this example, our final solution for this one is y equals to c1 times e to the rx, which is negative 3x, plus c2 times e to the rx again, which is negative 3x. And this is using case number 2. And remember, this is a general solution since no initial condition was given at the start of the problem. Hi everyone, we're back with our last example for today's second order linear differential equation. So we have here y double xn plus 64y equals to 0, and we can rewrite this equation into r squared plus 64y, or r squared plus 64 equals to 0. And if we subtract both sides with 64, we will get r squared equals to negative 64. And now we're going to square root both sides, of course, to remove the square on the left-hand side, remember, because we want to find the roots of this equation. We will get r equals to the square root of negative 64. But wait a minute, you all may seem confused right here, because we definitely cannot take the square root of any negative number, okay? So you cannot, if there's any negative number within square roots, you will not be able to solve it. But this is a situation of a complex number where you will be required using imaginary root. So you can break down inside the square root of negative 64 becomes negative 1 multiplied by 64. And keep this in mind, your square root of negative 1 will always becomes an I, okay? And so you can just take the square root of 64, a positive 64, becoming an 8, which by then r equals to plus or minus. Remember, you should put plus or minus since it's a square root of 8i. Or it will be better if I will write it in this form. So you'll notice later why I write it down in this form. 0 plus or minus 8i. So you know by now, we're gonna use case 3 since this has an imaginary root in it. And so why I write it down in this form of 0 plus or minus 8i is that because r1 in an imaginary root is equals to alpha plus beta I. And for r2, it will equals to alpha plus, or actually minus, beta I. And so, let's solve for the general solution for r equals 0 plus or minus 8i. We know that the general solution for case number 3 is equals to y equals to e to the alpha times x here, okay? And we know alpha is 0. So e to the 0 times x, it will just be 1, okay? So let's just write down 1. And inside the bracket, times c1 times cosine of beta x. And we know beta here is 8, okay? You see here, beta is 8. And so cosine of 8x because it's beta times x plus c2 multiplied by sine, and we're gonna do the same thing here again, beta times x, and we know beta is 8, so it will still be 8 times x. And so this will be our final solution or general solution to example number 4 today towards second order linear differential equation.